Hello, myself C.Kalshetti, Assistant Professor, Department of Electronics Engineering, Walchand Institute of Technology, Solpaur. Today, I am going to discuss the three-phase bridge inverter. Learning outcome. At the end of this session, students can analyze the three-phase bridge inverters. Three-phase bridge inverters are widely used for the variable frequency drive application and for the high power application such as HVDC power transmission. A basic three-phase inverter consists of three single-phase inverter switches, each connected to one of the three load terminals. A basic three-phase inverter is a 6-step bridge inverter. It uses a minimum of 6 thyristors. In inverter terminology, a step is defined as the change in the firing from one thyristor to the next thyristor in the proper sequence. For getting one cycle of 360 degree, each step is of 60 degree interval. This means the thyristor will be gated at a regular interval of 60 degree in a proper sequence so that three-phase AC output voltage is synthesized at its output. Two types of control signal can be applied to the power devices: 180 degree conduction mode and 120 degree conduction mode. So this is the circuit diagram of three-phase bridge inverter. It is the combination of three single-phase half-bridge inverter. It consists of 6 power devices T1 to T6 and 6 feedback diodes D1 to D6. Here the load is either star connected or delta connected. Three-phase bridge inverter is equivalent to three-phase half-bridge inverters arranged side by side. The three-phase load connected to the output terminals A, B and C of the inverter assumed to be star connected. In the circuit diagram, the numbering of thyristor is done in the sequence in which they are triggered to obtain the output voltage VAB, VBC, VCA at the output terminals A, B and C. There are two possible patterns of the gating the thyristors. In one pattern, each thyristor conducts for 180 degree and in another pattern, each thyristor conducts for 120 degree. So 180 degree conduction mode for the three-phase inverter. In this mode, each thyristor conducts for 180 degree. 3 thyristor remains on at the any instant of the time. Thyristor pair in each arm, that is T1, T4, T3, T6, T5, T2 are the turned on with a time interval of 180 degree. It means that T1 remains on for 180 degree and the T4 conducts for the next 180 degree of a cycle. When thyristor T1 is switched on, terminal A is connected to the positive terminal of the supply. If the T4 is switched on, terminal A is connected to the negative terminal of the supply. There are 6 modes of operation in a cycle and the duration of each mode is the 60 degree. The load may be either star form or delta form. Inverter switches of any leg cannot be switched on and off simultaneously. So it is the job of the designer that switches cannot be switched on and off simultaneously. Thyristors or IGBT are numbered in the sequence of the getting the power devices, and the sequence of power devices 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, 5, 6, 1, 6, 1, 2. Now, thyristor T1 is fired first. It will conduct for 180 degree and then turned off. Other thyristor in the same arm, that is T4, must be fired after turning off of the T1. However, T2 is fired after 60 degree interval from the firing of T1. Thus, the firing of the thyristor is The sequence is T1 to T6 with an interval of 60 degree between the two successive firing. The conducting thyristor in the different steps are as follows. Now step 1, 0 to 60 degree. In this step, thyristor 5, 6, 1 are in conducting state. In the next step, 60 degree to 120 degree, T6, T1, T2 conduct. In the next step, 120 to 180, T1, T2, T3 conduct. In this way, the sequence of thyristor is the 561, 612, 123, 234, 345, 456, 561, and the duration of each mode is the 60 degree. Analysis of three-phase bridge inverter with 180 degree conduction mode. Now, in this mode 1, the range of omega t is 0 to 60 degree. In this mode, T5, T6, T1 are in conducting state. Here, T1 and T5 are from upper half and T6 from lower half. So here T5, T6, T1 are in conducting state. So this is the equivalent circuit. Now, so here the Z equivalent is equal to Z plus Z by 2. This Z and this Z both are in parallel. Therefore, the Z equivalent is equal to 3Z by 2 and the circuit current I1 is equal to ES upon Z equivalent is equal to 2 ES upon 3Z. Therefore, phase voltage VAN is equal to I1 into Z by 2 is equal to ES by 3 and phase voltage VCN is equal to ES by 3. Phase voltage EBN is equal to minus I1 into Z. So, minus 2 ES by 3 and the line voltage VAB is equal to VAN minus VBN is equal to ES. VBC is equal to VBN minus VCN is equal to minus ES and VCA is equal to VCN minus VAN is equal to 0. Now, during mode 2, omega t greater than 60 degree and less than 120 degree, in this mode T6, T1, T2 are in conducting state. So, this is the equivalent circuit for the mode 2. Now, in this mode 2, the total Z equivalent is equal to 3Z upon 2 and the I2 is equal to 2 ES upon 3Z. So, here VAN is equal to 2 ES by 3, VCN is equal to minus ES by 3 and VBN is equal to minus ES by 3. VAB is equal to ES, VBC is equal to 0 and VCA is equal to minus ES. During mode 3, the duration of mode 3 is from 120 to 180 degree. In this mode, T1, T2, T3 are in conducting state. So, this is the equivalent circuit for the mode 3. Now, for this mode, Z equivalent is equal to Z plus Z by 2 is equal to 3Z by 2 and I3 is equal to 2 ES upon 3Z. So, for this mode, VAN is equal to ES by 3, VCN is equal to minus 2 ES by 3, VBN is equal to plus ES by 3 and VAB is equal to 0, VBC is equal to minus ES and VCA is equal to VCN minus VAN is equal to minus ES. Now, during mode 4, omega t greater than pi less than 4 by pi by 3, T2, T3, T4 are in conducting state. Now, this is the equivalent circuit for the mode 4. Now, in this mode 4, Z equivalent is equal to 3Z by 2 and I4 is equal to ES upon Z equivalent is equal to 2 ES upon 3Z. So, here VAN is equal to minus ES by 3, VCN is equal to minus ES by 3, VBN is equal to 2 ES by 3. So, VAB is equal to minus ES, VBC is equal to plus ES and VCA is equal to 0. Now, during mode 4, mode 5, in this mode, omega t greater than 4 pi by 3 and less than 5 pi by 3, and the T3, T4, T5 are in conducting state. So, in this mode, I5 is equal to ES upon Z equivalent is equal to 2 ES upon 3Z. So, for this mode, VAN is equal to minus 2 ES by 3, VCN is equal to ES by 3, VBN is equal to ES by 3, VAB is equal to minus ES, VBC is equal to 0, and VCA is equal to VCN minus VAN is equal to minus ES by 3. And last mode, in this mode, omega t is greater than 5 pi by 3 and less than 2 pi. In this mode, T4, T5, T6 are in the conducting state. In this mode, I6 is equal to 2 ES upon 3Z. So, VAN is equal to minus ES by 3, VCN 2 ES by 3, VBN minus ES by 3. VAB is equal to 0, VBC is equal to ES, and VC is equal to ES. Now, these are the phase voltage waveform. Here, in the mode 1, for the mode 1, VAN is equal to 2 ES by 3, VBN is equal to minus ES by 3, and VCN is equal to minus ES by 3. Here, these are the phase voltage waveform, and these are the line voltage waveform. Expression for RMS value of line voltage and phase voltage. So, VL is equal to 1 upon pi 0 to 2 pi by 3 ES square d omega t raised to half. Therefore, VL is equal to root 2 by 3 ES is equal to 0.8165, and the RMS value of phase voltage V phase is equal to VL by root 3 is equal to 0.4714 ES. What is the conduction angle of power devices in the 180 degree conduction mode? In the 180 degree conduction mode, each power device conducts for 180 degree. Therefore, the conduction angle for the power device in this 180 degree conduction mode is the 180 degree. These are the references.